Hey, it's Mr. Allred, and I'm here to talk about gradients. So if you're given a multivariable function, the gradient gives you the direction the function increases the fastest in. So I've got a little graph over here to try and demonstrate that with, or at least the idea. It doesn't have anything to do with the functions I've got, but here is the origin of this graph. So an x, y goes in, a z comes out. If you point in one direction, you're going up. You point in another direction, you're going down. So we talked about this with partial derivatives, that the derivative only is good enough for the point you're at. Now, the gradient is going to be a vector. Okay, so it's going to point you in a direction. Okay, so when you take the derivative, you can plug in a point, and you will figure out how things are changing at that point in a certain direction, because you can only take it with respect to one variable. But the gradient will give you a direction from that point to where you would head if you wanted to move the fastest. So we've got a little formula here. It looks like an upside down delta. It's pronounced del. It's not a real letter or anything. It's just a made up symbol. But del f equals the partial of f with respect to x, and that's put into an I component. So here we have the vectors, plus the partial of f with respect to y, and that's put in a j component. So that is for two inputs, one output. You could also have a partial of f with respect to z for the k component if you wanted to do four-dimensional, three input, one output. Okay, so that calculates del f, which is also known as the gradient. So an example we have here, f of xy equals x squared over 2 minus y squared over 2, and we're going to first of all find the gradient. Okay. So let's see if we can do that. So the gradient will be the partial of this function with respect to x. Well, that will be just x actually, so maybe I won't even need my parentheses, but that will be just x, because when I take the partial of x squared over 2, it'll be 2x over 2. It'll reduce to just x. And the other part, the y squared over 2, does not have an x in it, so it just goes to 0. So I've got xi. And then for the partial with respect to y, x squared over 2 goes away, and I'm left with negative y after the partial. So this calculates the this is the vector, and it's a generic vector that would calculate the direction if we were at any point we could move to increase the fastest. So what we're going to do now is we're going to take an actual point, and the notation looks like this. We're going to use the point square root of 2, 1 for xy, and we're going to plug it in. And we'll plug in square root of 2 for x, so we'll have square root of 2i. And then 1 for y, so we'll have minus j. So that's the direction if we were at the point, the xy point, square root of 2, 1, that we would move to start increasing this function the quickest. Okay. So it's a vector, so it's a direction. So we're given a point as a location, and the vector tells us which direction we'd move to change and increase the fastest. If you wanted to decrease the fastest, it would just be the opposite direction. So you'd have the negative gradient, or the opposite of that vector. Let's calculate another one down here. See if I can do it with still the formula up there. This is an xyz one, so we will have a 3 component. But f of xyz equals the natural log of xy plus the natural log of yz plus the natural log of xz. And then that will give us we're going to calculate the gradient from there, and then we're going to plug in a point. So first of all, let's calculate our gradient. So del f will be, we got to take the partial of this thing with respect to x. So natural log of xy, that would give us y over xy. Natural log of yz would just go to 0 because there's no x there. And then plus natural log of xz would be z over xz. You can tell this stuff is going to reduce. But that would be our I component. our j component, the partial of f with respect to y. So that would be the first two terms. So that would be x over xy plus z over yz. That's the j. And then the k component, that's with respect to z. So that will be the last two natural logs, because the first one doesn't have a z, it would be a constant and go to 0. But we'd get y over yz plus x over xz, and that would be the k component. So let me slide up, since we know we've used the right formula. Alright, so let's just clean this up first, since this is a general gradient. Let's see, this will be the y, and for the I component, the y's will cancel out, the z's will cancel out, so it'll look like 2 over xi, and the rest of them will look very similar. For a j component, it will look like 2 over yj, and for the k, it'll be 2 over zk. So that's the gradient, and if we pick an x, y, z point location, it will tell us the vector, which will give us the direction that we would move to increase the output the fastest. Not necessarily the most, but the fastest. So keep that in mind. Not where it's going to go up the most, but the fastest. Okay, so let's see here. So we're going to plug in the point 1, 1, 1. That's an easy one. So that would be 2i plus 2j plus 2k. So that's the direction I would move to make this thing increase the fastest, the most rapid. So that's the gradient, and that's how we calculate it and calculate it at a point. We'll see some other uses for it in a little bit.